Hi, my name is Brant. I'm presenting the impulse framework for momentously fast, general, and portable probabilistic programming via compiler augmentation. So Bayesian inference is a very important tool that infers hidden values from noisy observations by running a sampler to explore possibilities. And Bayesian inference is critical, especially when data are limited, indirect, or noisy. And probabilistic programming enables scientists to represent Bayesian statistics as code and run inference algorithms conveniently. However, one problem is code you want to write is usually not the code the sampler should run. And hopefully by the end of this talk, I hope to convince you that rather than pushing the burden of performance engineering the model to users, compiler can enable fast inference on natural code. And a scientist would love to write their model by directly transcribing their scientific formula like this. And then they call a probabilistic programming framework to automatically generate this loop. That's a sampler that runs this model repeatedly within a hot loop. There's a problem with this directly transcribed code that the expensive Cholesky operation is recomputed at every iteration, and there's no way for a general purpose compiler to eliminate this repeated computation. But taking a closer look as a human user, it's possible to decompose this Cholesky expression into a square root of a loop variant factor times a Cholesky of a loop invariant matrix, so we can factor out the entire Cholesky expression outside the model, so it's only computed once. However, today existing frameworks require the user to rewrite the model by hand like this, and this requires expert analysis to identify this redundancy, let alone do this rewrite. And people often have to understand what these helper functions are doing, and this can be extremely hard in practice. So one natural question is, why can't existing framework fix this redundancy automatically? The reason is existing frameworks resolve their probabilistic semantics before anything reaches a compiler. So the compiler can do nothing about this kind of redundancy. And here's an example of the previous example that's lowered within the compiler, and the compiler will have to figure out like which operation are the Cholesky and which are its gradient. And this requires an intractable amount of analysis to do this rewrite at this round abstraction level. And we ask two key scientific questions here. Can we preserve probabilistic structure in compiler IR? And can a compiler automatically enable fast inference from natural code? And we propose constructing first-class compiler primitives within the compiler, so the compiler understands the probabilistic structure preserved by this kind of high-level IR. And having this first-class IR has two benefits. One is we can run existing optimizations to run on a probabilistic code that's written in a natural way by the scientist, and one can run novel probabilistic optimizations that no existing frameworks can do. One such novel probabilistic optimization is Sample-Invariant Code Motion that addresses exactly the redundancy we showed in the earlier example. One can first do sample dependence analysis automatically within the compiler to identify such repeated deterministic computation by statically analyzing the code that this Cholesky is taking a sampled parameter that's loop variant and a matrix that's loop invariant. And the sample-invariant code motion can apply rewrite patterns that a general purpose tensor compiler will never do, because this is adding computation by adding a square root. And we as a compiler understand the probabilistic semantics that we will have to run this code for millions of times so we can benefit from doing this kind of rewrite. And we perform evaluations on multiple case studies. Our results include just by running standard compiler passes on this high-level IR, we can get 8 to 60 times x speedup. And if we can also enable the probabilistic specific optimizations like sample-invariant code motion, we can bump this speed up to 190 times. And on standard benchmarks like PPL bench, we are faster than 3 popular frameworks like NumPyro, who's also based on MLIR, and we are faster than Stan, that's very popular in community, and we can also outperform Turing.jl. And we also apply this framework to a real astronomy workload that infers an image of a black hole from telescope measurements. And this is a very hard inference problem that requires a GPU to run efficiently. And Impulse can fold an emph operation hidden behind multiple layers of library calls into one pre-computed matrix product, so it only has to be evaluated once. And doing this manually by hand is extremely hard because people will have to understand that the Sky model library is calling a fast Fourier transform library, and there is such redundancy. And we are able to achieve this 3.7x speedup by doing probabilistic specific optimizations enabled by this high-level IR. And that concludes my talk. I just introduced a new probabilistic programming framework called Impulse, and we address the problem with writing natural code by a scientist because they want to write exactly what they want instead of performance engineering their code. And we performed a Bayesian study to show we are able to achieve 3.7x speedup on a state-of-the-art GPU black hole imaging workload. Thank you so much.
Thank you. Any questions?
Thanks so much. Very cool. I have 2 questions. One is, for the experiments that you did, how sort of specific were the rewrite rules that you needed to incorporate to get the wins that you had? Or would they show up in any kind of scientific computing optimization pipeline?
For this, for example, for this black hole imager that we just showed, it requires a fast matrix, fast Fourier transform rewrite rule, and after that fires, we need a general matrix multiplication rewrite rule. Like 2 rows are fires like sequentially, so we can like move the entire matrix product out of the loop. So and also we have 7 other loops that we did ablation studies on. If you're curious, I encourage you guys to read the abstract. Thank you.
Thanks. Can I just quickly ask one more question? How specific is this to probabilistic programs? It seems like a lot of workflows, for example, in machine learning with deterministic neural network models, you could imagine doing something like parameter invariant code motion or something like that. It seems like it's really about sort of lifting parts of a function that don't depend on the thing that's dynamically changing every time I call the function out to the top level. Like, how much is this about probability versus about that kind of pattern?
Thank you. That's a great question. And I would like to show you this early example here. So by specific to the probabilistic programming here, the alpha is a sample parameter that's highly related to the semantics of we are doing Bayesian inference here, because this alpha changes per iteration in this inference algorithm, because at each iteration we kind of perturb it by a little bit. This is specific to inference algorithm here, and this requires knowing like the semantics of probabilistic programming to do. And similarly, I can absolutely imagine doing this on a machine learning semantics if one also have this kind of high-level semantics, which I doubt like already exists. But what we are doing here is really dependent on the semantics of probabilistic programming. I hope this answers the question.
Other questions?
So 2 related questions. One is, does this need an IR, or could you just be doing source level transformations on the original language? And relatedly, have you compiled multiple probabilistic programming languages to this?
In future work, we would love to compile other languages to this. And so doing this at source level is extremely hard because, for example, in this example, the FFT is like hidden like multiple layers down the library cost, and we would have to either inline the library implementation to code, or we modify the library source directly, and either way would be extremely hard. And if we do this compiler-style transformation, compiler can inline these operations here, and we only need to do this kind of syntactic matching, so we can do this easy rewrite without having to implement an extremely complex source level rewrite engine. That would be very hard.
I see, that makes sense.
Thank you.
All right, I think that's all the time we have for questions. So let's thank everyone for participating, and thank you to our wonderful judges.